Hello, this is the second video of a polar coordinates series for OCR Pure Core Further Mathematics, and we will see how to sketch curves with polar coordinate equations. A sketch of a curve shows its shape, symmetry, and other important points like intersections. To do this, we will work out the coordinates of a few points on the curve and then try to connect them in a smooth way. We might consider how r changes for different theta, particularly looking at the values of theta for which r equals 0 or is possibly a maximum or minimum. We would link this to our previous experience of drawing graphs of trigonometric functions. It is sometimes easier to sketch polar curves than Cartesian curves, especially when there is rotational symmetry. We'll consider the following examples of r equals some function of theta. If you have a graphical calculator, then you may be already used to plotting graphs and drawing sketches from it. So, considering the general case for r equals some constant k, let us just pick k equal to 4 initially. This point, this point, this point, and this point will all be on that curve. If we try to link those up in a smooth way, or we could plot some more points, for example one there, we can see that it will be a circle. Using GeoGebra, we can see the effect of altering k. You can see that, as we might expect, as k decreases down to 0, then that curves are still all circles and the radius depends on what k is, but the shape will not alter. Polar curve r equals 3, 1 plus cos theta. Let's build a table of values before we sketch. We know that cos theta lies between -1 and 1. So this will help us work out these values, and it might be useful to sketch a curve of cos theta just to help us. When theta is 0, cos theta is 1, and so r will be 6. Moving along, pi by 3, we would find that cos theta was a half, and therefore r would be 4.5. At pi by 2, theta is 0, so r is simply 3. At 2 pi by 3, cos theta will be minus a half, and therefore r reduces to 1.5. When theta is pi, cos theta will be -1, and r will be 0. Thus for this half of the curve, we can see that it probably looks like that. Moving on, 4 pi by 3 would give us an r value of 1.5. 3 pi by 2 would give us 3. And then if we were to consider the next point, we'd be back up to 4.5. We could write that as minus pi by 3. Thus, putting those points in would indicate that the curve has a symmetry and looks something like that. So when it is drawn during a graphing tool, we can see that there is indeed symmetry, and that the r values oscillate between 6 and 0, in other words, plus or minus 3 either side of 3. and that if we were to put in higher values or any different value of theta, the curve would just repeat. So let's see what happens when we change those values of a and b. Starting with the a equals 3, b equals 1, which is the curve we've just sketched. As a increases, you can see that that just affects the size. Let's consider changing b. As b increases, you can see that the shape becomes increasingly more circular. If you like, it loses that dimple. When b is less than 1, you can see then that there is that additional loop. If we wish to build up a table for r equals 3 plus sine 2 theta, it would be again useful to bear in mind the shape of the sine curve and to think about the range of values that sine 2 theta can take. If we were to build up in the same way, we would find that we had values such as this. And then we might spot the pattern. In a similar way, we could build up a sketch of a graph by plotting points and then smoothing the curve as best we can between it. We can see here that the value of r oscillates between 2 and 4 for this curve. If we are to see what happens as a, b and c vary in the more general form of r equals a plus b sine c theta, then changing a just changes the shape of that curve, like that. Changing b like that, and c changes the orientation. If we were to set a to 0 and then in effect just look at curves of the form r equals b sine c theta, let's just make b a little larger so we can see what's going on. These produce a family of curves called rhodania or rose curves, and you may wish to investigate the relationship between c and the shape of the curve. So if c is 1, or indeed minus 1, and then when c is 2, and then try minus 2, for c at 3, and c at 4. In the next video, we will convert coordinates between Cartesian and polar forms.